Hi everyone, this is Mrs. J. Today we're going to be solving polynomial equations, but first please pause the video and give this warm-up a try. Alright, go ahead and take a look. Just remember the number that we're putting in the box is the opposite of what you see in the factor. It'd be the 0 of this factor. So remember we just add vertically and then we multiply by the box number. Add, multiply, and then here's our quotient plus the remainder over the divisor. This is in the warm-up today because we're actually going to be using synthetic division as part of our process of solving today. So it's super important that we remember this skill. All right, so in the last lesson, we talked about different ways to factor polynomials. So factoring is going to be our first option if we are solving a polynomial equation. If something is factorable, we should use that method. It's always going to be the easiest and quickest method. So if it says find the zeros of the function, we're asking for the x-intercepts, and that means that we set our y value equal to 0. So it's always going to be the first thing that we do. And then again, we should try to factor if at all possible. Here, we always check for a GCF first. I see that there is a GCF of 2x, so I'm going to divide it out and place it out front. Notice I'm not dividing both sides. You can never divide both sides by a variable. So I'm just going to factor it out. So minus 6x plus 9. And then we're going to look at the remaining trinomial here, and we can see, well, it's a perfect square trinomial, but we could also use magic x to factor it. So what multiplies to make 9 and adds to make -6? So we have -3 and -3. So that gives us x minus 3 times x minus 3, or we could say 2x times x minus 3 squared. Now from here, we would simply use the 0 product property. We set each factor equal to 0 separately. So I'm going to set 2x equal to 0. Here, I know we have this factor twice. We only need to set it equal to 0 once. So x equals 0 and x equals 3. Those are going to be my two solutions. I am going to make a note here, since I noticed that we have this factor squared, or again, it's this factor twice. Remember when we were graphing, we talked about this concept of multiplicity. So this has a multiplicity of 2. Because now that we have the zeros, we're actually going to sketch a graph. So we're going to start with our with plotting our zeros. So let's call this 3. And then here's the other one at 0. And then remember, when we have a multiplicity of 2 or an even multiplicity, we're going to have a touch and turn. So it's going to touch the x-axis and turn around. And now we can go through the rest of the process for graphing. So this is really good review. Our leading coefficient is positive, so that means the right side of my graph is going to go up. The degree of my graph is 3, which is odd, which means the end behavior is opposite. So this side is going to go down. And then I just need to connect the dots with my zeros. So I'm going to touch and turn, and then I go through here, and then I'll just continue on to negative infinity. So again, this process of solving, we already know how to factor something like this. So now we're simply factoring and using the 0 product property to solve for x, which are the x-intercepts. And then this process of graphing is also something we already know how to do. So this is kind of tying it all together. So we use factoring and we review graphing as well. All right, let's try another one together. So first, remember, we're going to set this equal to 0 because we're finding the zeros. One thing we can do, I do notice that there's a GCF of -2, and since it's just a constant, instead of factoring out, which is also completely fine, I'm actually just going to divide both sides by it. So again, as long as there's no variable, you can do this. So that gives us positive x to the 4th minus 8x squared plus 16. So this is what we called a quadratic type equation. quadratic type, because we can see that the exponent here is double the exponent here, and then we have this constant. So for something like this, we would factor it as if it said this, plus 16, which we could just do some magic x. What multiplies to make 16 and adds to make -8? That'll be -4 and -4. But instead of saying x minus 4 times x minus 4, we need to adjust our exponents for our first terms. So if it needs to multiply to make x to the 4th, these are both going to be x squared. All right, from here we should always ask ourselves, can I factor more? And for both of these, we can. We can use difference of two squares. So for both of them, our a value is going to be x, our b value is 2. So we have x plus 2 times x minus 2. Those are the factors of this one. And we're going to do the same thing again here. So you can see that we actually have x plus 2 squared and x minus 2 squared. So if I want to finish solving for the zeros, I'm going to show my zero product property. Remember, this is a step I would like you to show. And so we get two zeros, positive 2 and negative 2, but they both have a multiplicity of 2 because both of them had squared factors. So that is going to affect what happens when we graph. Okay, so let's plot the information we have. Here's -2. Here's positive 2. Our y-intercept, which we can plot. Remember, we get the y-intercept by setting x equal to 0. So f of 0. If you look at the equation, this term will turn to 0, this term will turn to 0, and we're just left with -32. So I'm just going to plot that down here. Again, it does not need to be drawn to scale at all. Okay, let's go through the process. If you look at the original function, my leading coefficient is negative, so that tells me that the right side goes down. The degree is 4, which is even, which tells me my end behavior matches. So the left side also goes down. We know that at 2, we're going to have a touch and turn because of the multiplicity. And at -2, we will also have a touch and turn. So let's put it all together. So I go up to 2, I touch and turn. I know I need to go through this y-intercept. I go up to -2, I touch and turn, and I continue on. So this is what my graph looks like. The zeros are -2 and 2, but they each have a multiplicity of 2, which is why you see those touch and turn behaviors on the graph. And this is also a really good review of how to factor that quadratic type equation. All right, go ahead and pause the video and see if you can give this one a try on your own. All right, go ahead and check your work here. So you can see first, I set my equation equal to 0. I factored out 5x. Remember, we're never going to divide out x altogether because then you lose the solution. So we're going to leave it as a factor. And then you can factor this remaining trinomial with magic x. We have two answers, 0 and 4. But 4 has a multiplicity of 2 because of the squared factor. So when you go to graph it, it looks like this. We have that touch and turn at x equals 4. All right, here I have one more for you to try on your own. So again, please pause the video. All right, go on and check your work here. So first thing that I did after I set my equation equal to 0 was I divided both sides by -1, just to make my leading coefficient positive. So it's a little easier to work with. Then, since there's 4 terms, I factored by grouping, which you can see right here. There's that common factor of x plus 2, so you can group the coefficients into its own factor. And then you can factor even more with difference of two squares. So x plus 3 times x minus 3 times x plus 2. So here we have these three factors, which gives us these three zeros, each with just a multiplicity of 1. So there's my x-intercepts. My y-intercept is at 18. And then the right side of my graph is going to go down because my leading coefficient is negative. The left side should be opposite because the degree is odd. And then from there, it's just a matter of connecting the dots. All right, so now we're going to talk about what we're going to do if we need to solve an equation that's not factorable. So if you have an equation that's not factorable, we're going to need what's called the rational root theorem, which will give us a list of potential answers. So this list of answers is going to be all of the possible combinations of all of the factors of your constant term over all of the factors of your leading coefficient. So again, this will just give you a list of possible answers. So after you list out the possible answers with the rational root theorem, you're going to start testing your answers with synthetic division. And you know that one of the answers works when you get a remainder of 0. So once you have a remainder of 0, you have at least one of the answers. You're going to look at the remaining polynomial and see if you can factor it, or if it's a really difficult problem, you'll have to use the rational root theorem all over again until eventually you find all of the possible zeros. Okay, so let's give one of these a try. So here I look at this polynomial. You could try to factor by grouping. It wouldn't work. This is just not factorable. So I know I need to use the rational root theorem. I like to write RRT to give me a list of possible solutions. So first I'm going to list out my p-values. My p-values are all of the possible factors of 20. So that'd be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. And then I can list out my q values, which is just the factors of my leading coefficient, which is just 1. And then we're going to list out all possible combinations of this p over q, which we could see are just the p values. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. So if you look, we have 1, 2, 3, 4, 5, 6 times 2 for the minus. So we have 12 possible answers. So from here, we're just going to pick one, and we're going to start testing it with synthetic division. So I'd say in terms of picking which one to test, a lot of it is kind of just luck. I would say like we probably don't want to start with plus or minus 20 or plus or minus 10 or probably not even plus or minus 5. I like to start with some of the smaller values first. So let's say we want to test x equals 1. Maybe we'll see, is this a potential solution? So if I want to test x equals 1, I'm actually going to use 1 in the box because these are zeros. They're not factors, they're zeros. So whatever you're testing is the number that goes in the box. And then I'm going to list out my coefficients for the synthetic division. And you're going to be doing a lot of synthetic division with these types of problems. So it's really important that we're quite comfortable working with our synthetic division. Okay, so I've done my synthetic division, and I see that the remainder is not 0, which tells me that positive 1 doesn't work. Okay, let's pick another number to try. Let's test x equals negative 1 and see if that works. You don't have to go in order. You could just pick one that you feel like might work and hope you get lucky. So again, list out your coefficients. So add vertically, multiply, add vertically, multiply, add vertically. All right, so here we have the remainder of 0, which means that x equals 1 is a solution. So I'm going to maybe put a big circle around that so I remember that that's a solution. And then I'm going to take my remaining polynomial, so x squared minus 9x plus 20, which I got, that's the quotient of my long division. So remember, you always start with, your first coefficient is always going to be 1 less than the original problem. And then we're going to set that equal to 0 and see if we can solve this by factoring. So luckily this one is factorable. What multiplies to make positive 20 and adds to make negative 9? Negative 5 and negative 4. So x minus 5 times x minus 4 equals 0. And then we can show our zero product property. So we get x equals 5 and x equals 4. And then from up above, we also know that x equals negative 1 was one of our solutions. So here we have 3 solutions, negative 1, 5, and 4. And all of that came from our list of possible answers that we found using rational root theorem. All right, let's try this one together as well. So here, if you tried to factor by grouping, which you should, there's 4 terms, you'd find that it's not factorable. So we need to list out our potential zeros with the rational root theorem. Again, our leading coefficient is 1, so when we do the p over q, the q value will just be 1, so we don't really have to worry about it. So we're essentially just listing out the factors of 24. So we have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. All right, so let's start testing. Let's test x equals 1. Let's just see what happens. So we have 1, 1, negative 14, negative 24. So we multiply, add, multiply, add, multiply, add. Our remainder is not 0, so x equals 1 is not a 0. All right, let's try another number. Let's try negative 2 and see if that works. Okay, so we multiply and we add. We multiply and we add. We multiply and we add. Oh, here we have that remainder of 0, which means that x equals 2 is a solution. Sorry, x equals negative 2 is a solution. So I'll box it up here. And then I'm going to look at the remaining polynomial, x squared minus x minus 12. And I got that from these numbers for my quotient. And I'm going to set that equal to 0 and see if I can finish solving. This one is also factorable. So what multiplies to make negative 4 and adds to make negative 1, negative 4, and positive 3. So x minus 4 times x minus 3 equals 0. Please show your zero product property step. And we get x equals 4 and x equals negative 3. So here we have 3 solutions. X equals negative 2, x equals 4, and x equals negative 3. So make sure to box all of your answers at the end. All right, here I have one for you to try on your own, so please pause the video and give it a shot. Alrighty, so here you can see the list of possible answers that I created using the rational root theorem. So this is all of the possible factors of 10 over all of the factors of 1. So I tried x equals 1, and we got that remainder of 0, meaning it's a solution. Then the remaining polynomial is x squared plus 3x minus 10. So I set that equal to 0, and I solved by factoring. So I got 2 more solutions. I got negative 5 and 2, and then 1 is also a solution. So make sure you list all 3. Okay, here's the last example. Pause the video and give it a try. Alrighty, go ahead and check your work here. This is the list of possible answers. So I tried negative 2, and I found that the remainder was 0, so that means negative 2 is one of my solutions. Here's the remaining polynomial, so 1x squared minus 7x plus 12 equals 0. And then I solved this by factoring, and I got 2 more solutions, positive 4 and positive 3. All right, that's all for today's video. Thank you so much for watching.